Good morning and welcome to STEM Ambassadors Live, and I'm joined today by Peter Samain. Now, Peter is going to talk to you about a career in engineering and construction. So I'm going to hand over to you now, Peter. Thank you very much.
Okay, thank you. Hopefully the technology will work. We'll try and share screen. Hopefully you can see that all right, can you? Okay, so my name is Peter Samain. I'm an engineer. I've worked in construction most of my life. I actually trained as a mechanical engineer eventually, but most of that mechanical engineering was associated with the construction industry. Here's a few images of some of the things I was involved with. But engineering is a wide subject. So while I worked on car plants down here and large scale engineering installations for everything from breweries to petrochemical plants, I also had a little bit to do with the Angel of the North, where the sculptor needed engineers to design all of the things that would hold the sculpture up in the north of England in great high winds on top of a hill. And of course, these great big wind sails here would want to turn it over. So you can be involved with all sorts of things. So I wasn't particularly good at school. I didn't leave school with a lot of qualifications. So minimal GCSEs when I was 16. And I then spent quite a lot of time, not because I had to, because I actually enjoyed it, working as a site apprentice, which means I was on site. I was screwing pipes together. I was actually a pipe fitting apprentice. And then I went on to what they call cross the bridge, which means become a technician apprentice. And I did some night school and I did some city and guilds, which are rather like BTECs and diplomas. And then I migrated through that into a Bachelor of Science degree and then subsequently into a master's degree. Of course, you don't have to do all that, but as I say, I was interested in doing it. I moved to America, actually became an American citizen while I was there, but I moved to America to work in America for about 7 or 8 years. And then by this time I got married and I'd had children, so I came back to the UK. And then I worked for an international company and I really was working all over the world. And I'll show you some of the places I worked later on. I moved to East Asia as part of that to work in China and various other places. And then I retired a few years ago and I started my own little consultancy business, which I still run, but it's really just me helping people out that I knew along the way or I've known along the way. So it was a longish journey, but it was really worth it. I never stopped earning money, which is great, and I never stopped learning. And of course, you know, nowadays I didn't actually come out of the university with a great big bill, which obviously because I was sponsored by what would now be graduate apprenticeship style training. So here's some of the projects I worked on. We won't get too bogged down in all of them, but I mean, this is a very large car plant. No, it's not, that's Hactol, sorry. That's a very, very large air cargo handling terminal in Hong Kong. This is a large car plant, that's in Thailand. We'll talk about this one a bit later. That's a very large research facility in London. This tunnel is underneath the Olympics area in London. We had to underground all the main power supplies for the site in a great big tunnel with a little train running down it. That's another car plant. That's Toyota up in Derbyshire, where they make the Toyotas in the UK. This is interesting. This is the fusion tokamak jet in the Cullen Laboratories in Oxfordshire. And your generation will crack fusion. We won't go into it all now, but if we can make that work, that will solve all our energy problems. It's basically energy by fusing atoms together. So it's quite a difficult thing to do, and we've been at it for a while. So it's a very portable profession. I took it all over the world, or it took me all over the world, I should say. It doesn't have to if you don't want it to, but it can, and you get to meet all sorts of interesting people in very, very interesting surroundings, doing interesting jobs, usually with a bit of challenge thrown in as well. So I said I'd tell you about some of the places I've worked. So I spent a lot of time in East Asia. So not unsurprisingly, there's quite a few projects dotted around China and Hong Kong, a little bit in Australia, not very much, quite a bit down in Thailand, a little bit in Malaysia. This was East Africa. This was mainly what they call audits on primarily distilleries and breweries, funnily enough. And the other big area that I spent a lot of time is Eastern and Central Europe. So I did quite a lot of work in Russia before the Soviet Union broke up, and then just after it broke up. They were primarily things like aircraft hangars. And then in Central and Eastern Europe, that was primarily data centers and various other sorts of factories. And then, of course, in North America, because I lived there a long time, I was working primarily in the nuclear power industry and then subsequently the car manufacturing industry. So they were the two things I spent a lot of. And I traveled, there's a lot more red dots I could have put on North America. I traveled all over North America, from Tennessee to California and right up to Wisconsin, New Hampshire, Maine, and a little bit down in Florida. So did a lot of work all over North America. Here's a few things for you to think about. We needn't labor too many of them, but this is an interesting statistic. Only 6% of the engineers in the UK are female. It's about the lowest percentage in the whole of Europe. Even countries like Latvia and Bulgaria, much, much smaller than us, have sort of 30% of their engineers are women, 40% in China and 55% in Russia. So we're missing out on a big opportunity here, because half our population, more or less half our population, who may well have an interest in engineering, they just don't come into it. Why do countries become successful? Well, there's an interesting quote here about not having too many lawyers and not enough engineers. But if you take a country like China, until not that long ago, most of the people who ran the country, the Politburo, which is the thing that runs the country, had science or engineering degrees. So they understand what it takes to develop a country. And they have built thousands of miles of railway, highway, power stations, all sorts of infrastructure, and turn themselves into a incredibly successful country in the space. I mean, I went to China in the 1980s for the first time, and it was a pretty impoverished agricultural country, and there were a lot of very poor people there, and there still are, but they've dragged themselves up by their bootstraps. Quite extraordinary. Okay, so if you ask yourselves what all these people have in common, for the reasons I was alluding to earlier, most of them are men, which is a bit unfortunate. There is one lady there. So if you ask yourselves quickly what they all have in common, and I won't spend too much time keeping you guessing, they're all apprentices. They all started out as apprentices. And there they all are. Stella McCartney was an apprentice tailor. Joe Sugg was an apprentice thatcher, believe it or not. Alex Ferguson started out a typewriter manufacturer. Elvis Presley and George Harrison were both apprentice electricians. Alan Titchmarsh, not unsurprisingly, was an apprentice gardener. This man designed the Spitfire, R.J. Mitchell. That's the famous plane that took us through the Second World War. And he started out making, as an apprentice, making locomotives, steam engines. So here's just a few more images to illustrate the breadth of what engineers in the construction industry, and that's my industry. So things like the Gherkin, which you've probably seen in London. This is a very big football stadium in Germany, the Allianz Stadium. This is the Bird's Nest, which you may not have seen. It's a quite extraordinary stadium in Beijing that was built for the Beijing Olympics. The Chinese engineers who worked on it said it wouldn't stand up, actually. It was kind of interesting, and they put it through a design audit, which came out with the right answer at the end of it. This, of course, is the Sydney Opera House. There's a long story to that, which I won't bore you with now, but basically the architect resigned halfway through the job. So the engineers ended up getting it built, and it's an extraordinary building in very, very many ways. These concrete shells, no one had ever built anything like that before. It required a whole new set of design algorithms to be developed and so on. And then you get oddball buildings like this, where the center of gravity of the building doesn't appear to lie over the foundations. It looks like it should fall over. That's the CCTV tower in Beijing. And then things like offshore platforms. I think that's Ravensburn out in the North Sea. Now, because you're the generation you are, you'll recognize that when I started, it was all pencils and pens and bits of paper. That is obviously no longer the case. All building designs of any size are now built, designed in computers using three-dimensional modeling. And this is a good example of various models of various buildings, and everything goes into them, the pipes and the wires and the steel and the cladding and all that stuff. So you can see whether it all fits and works and all the rest of it. So let's see if this works. This is a job I worked on. It's one of the last jobs I worked on. It's the Francis Crick Institute in London. This is it down here. That's Euston Station along there. That's where all the cross-channel HS1 high-speed trains come into Euston. This is the British Library, which is a modern listed building. So it was shoehorned into a very tight site. 1,500 researchers work there. It's run by a very famous man called Sir Paul Nurse, and it's the premier medical research facility in the UK. So let's see if this will work. He said, holding his breath. It may not. And if it doesn't, I can only apologize and tell you what it would have shown you if it had worked. Aha, here we go. So what this is we put a parametric model, a full three-dimensional model together in about 2011 to illustrate the building and design the building.
You need to just drag it over.
Oh, I'm sorry. Can you see that now?
Yep, got it now.
Okay, good. So on the left-hand side here, this is actually a fly-through of the model. So it's a three-dimensional model, animated, pretending somebody's walking through the building. On the right, 5 years later, this is the building that's been built. It's the real building. This is a drone that's being flown through the building, taking the exact same route that we took when we did the animated fly-through at the design stage. I have never worked on a job that has turned out so accurately similar to the original design. What tends to happen in construction is things change, people add things, people move things, people decide they don't like something. But on this job, because we'd done such an enormous amount of work on the modeling and cleared all the models with the client and the construction company, pretty much what was in the model is what got built, as you can see. So this is the real building, this is the model. What you're looking at here is a very big atrium space in the middle of the building that runs right the way up through the building, and there's a lot of open plan congregation space. When you're in the research business, you want people to talk to one another, you want them to cooperate and coordinate their activities. We're now walking down the elevated walkways in the atrium. These are the lab spaces, the research cells where all the hard work's done. And there's quite an extraordinary picture in a minute. They managed to get someone sitting in one of these. This guy, this is the man that was sort of the model was based on, I think. Extraordinary similarity. These are the bridges, the crosswalk bridges between these walkways that link the laboratory spaces. There's 4 layers of laboratory space. About a third of the building is actually underground to keep the elevation so it didn't stick up in the air too much. So what you're looking at is rather like an iceberg. There's 2/3 of it sticking up above the ground and 1/3 of it is below the ground. We're now coming, we're driving away from it, parallel to Marylebone Road, actually. This is the roof. Now it's got, I can't remember how many thousands it is, but it's got thousands of photovoltaic cells. The whole of this black space on the roof is photovoltaic cells. It's about 5% of the maximum load of the building. It's a very high power usage. So that is that. Let's see if I can take us back to where we were. Hopefully that will. sure that's the right one. Sorry, bear with me. Right, can you see that okay? Hopefully you can.
Yep.
Okay, well, I've got one more video I want to show you. This is the Millennium Bridge. You probably weren't old enough to remember it, but in the year 2000, this very expensive, very carefully designed bridge that spans the Thames between St Paul's and the Tate Modern. It's a footbridge, doesn't carry any vehicle traffic. I'm going to have to do the share thing again. Hopefully it will work. Can you see that okay?
Yes, it's loading.
Good, right. So what we're looking at here is this is the opening day of the bridge. It attracted, well, about 2,000 people on the bridge on the day. This is a timer that's running through the first few minutes of that full-scale occupation. And fairly quickly, as you can see, the bridge starts to, it's harmonically vibrating, it's kind of what it's doing. And very quickly, you get this interesting human response where people are starting to be in step with the movement of the bridge, and of course, in step with one another. So it almost looks like they're dancing. And as a result of this, it became known as the Wobbly Bridge. It was shut the same day. So you can see all this cable stays here are moving. There's no danger here. This is not going to fall down. Nobody's going to get hurt. But obviously, it's quite disconcerting if you're on the bridge. So let's go back to where we were. I think it's here. Can you see that all right?
Yes.
Right, so that's a bit of a problem. We've built this very expensive bridge. It's moving around. We had to shut it. What are we going to do? So you might want to think about what we did or what needed to be done. I've asked this question quite a few times to various schools over the years. And most people come up with a perfectly rational solution, which is to stiffen the bridge. Now, to stiffen that particular bridge, you would need to put some fairly significant pylons, some great big tower things sticking up in the air. You'd have to link those into the horizontal sections of the bridge, and you would you'd fix the problem, no question about it. But you turn it into something that's totally different to what the customer bought and what the architect designed. The problem here is something that is very well known about. It's a 2,000-year-old problem. The Roman army used to break step when they crossed a bridge because they knew about something called unified footfall, which means that you can set up a sympathetic vibration in the bridge simply by virtue of walking across it. And that's exactly what happened here. Bridge design codes up until this particular occurrence didn't recognize that as a design case. So it didn't get thought about at the design stage. It should have been, but it wasn't. All those codes have been changed now, needless to say. There's no way the people who paid for that bridge were going to put up with a load of supplementary scaffolding being put on it to stiffen it. So I'll have to tell you, because we're recording this, I'll tell you what the answer is, but your teacher can pause this if she wants to, or they want to. We had to put things called mass dampers, and well, tuned, dynamic and mass dampers. So there's some very, very heavy bits of stuff hung off the bottom of the bridge. If we just go back and look at the bridge, so you wouldn't see them, but they are suspended underneath these sections of bridge. And they dampen in the way that a dampener does in a car. They dampen the vibration. And if you walk across it now, it is absolutely solid. We did a test run after we'd done the fix. Late at night, 2,000 employees of the firm that I work for went on that bridge and tried to replicate the problem that you saw in the video. And we couldn't do it. It was so stiff, we couldn't get it to move at all. So we were happy that we'd fixed the problem. The reason we did it at night was we didn't want the local papers taking photographs of all of us prancing around on the bridge. So that's the solution to that. Right, so moving on, I often get asked, what do you need to know if you're an engineer? Well, here's my little list, and we don't need to go through them all, but you certainly need to be able to think for yourself, and you learn to think for yourself during the course of your career, even if you're not very good at it when you start. You've got to be able to work as a team. You know, we don't need a lot of divas on construction jobs. And then you've got to be able to make mistakes and then do it better. Sweat the details. There's a famous case of a bridge failing in America where one bolt literally failed and the whole bridge, footbridge in a casino, failed with some rather unfortunate results. And that was simply because of you know, people not understanding who was responsible for designing things. Ability to focus, yeah, one problem at a time. You can't solve all the problems all the time. I used to have a boss who used to say, if you're going to eat an elephant, you need to do it one mouthful at a time. And while that sounds a bit strange, it is actually quite a good rule. Okay, and finally, what have I learned? Well, if I can do it, anybody can do it. That's for absolute certainty. You need to be able to, and this is true of most things in life, stick at things, put some energy into it, and focus on things. That's an important attribute for achieving things generally. Again, if you do something like an apprenticeship or anything else for that matter, but education, 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 never stop learning. I'm still learning stuff now, and I've been doing this for 50 years. You keep an open mind. There's always stuff out there that you didn't know. Figure things out for yourself. Yeah, that's a good rule. Received wisdom can sometimes be wrong. If I had £1 for every time somebody said to me, or we do it like this because we've always done it like that. And then you say to them, well, why do we do it like that? And they can't actually explain to you. It's just, that's the way it's always been done. So we'll do it that way again. And quite often that's a perfectly valid thing to do, but it's good if you know why you're doing it. So always ask the question. Listen to the other person. Nobody has all the good ideas. So it's listening is a very good skill, which I think we're probably less good at now than we used to be. It's a big world and we don't understand one another well enough, and that's true. You know, it is a small world in terms of traveling distances and times, but it's a big world when it comes to understanding the other person's point of view and different cultures, different histories. So try and keep an open mind about that. And a sense of humor works wonders. Even if you don't speak the same language, I've had some extraordinary laugh out loud moments with people who don't speak the same language as me, and I don't speak the same language as them, but somehow human beings will find some humor, and if you can, it's great. So I think that's me done. So if you've got any questions, if I'm there, I'll answer them. If not, then you can write them down. I'm sure they can be sent to me and I can answer them. Thank you.
That was great, Peter. Thank you ever so much for that. That was really, really interesting. So I'm going to stop the record now.